Okay, today's video we're going to take a look at how we can use the second derivative of a function, which is going to give us information about how the velocity is changing, whether the velocity is increasing or decreasing, to give us some information about the concavity of the original function. So kind of reviewing what we've been talking about so far, if you know that a derivative has a positive value, the derivative has a positive value, then you know the graph of the function is increasing. Okay? And if we know that if the derivative is negative, then it would be decreasing, the original function. But what we want to know beyond just the fact that it's increasing or decreasing is about how it's increasing. Is it increasing at a constant rate, which would make it linear, increasing at an increasing rate, which would make it concave up, or increasing at a decreasing rate, which would mean it's increasing but concave down. And so basically we're just looking at the curvature of the graphs. And again, we can look at this by looking at what's happening in terms of your review of pre-calc definition of concavity, and then how we're going to use the calculus definition of concavity and the second derivative. So here we have a curve that is increasing, but clearly both of these examples, the curve is increasing at different rates. And so what we're going to look at is what is actually happening. And if we look at the tangent lines, so if I draw in, I'm just going to make this a little bit more bold for you. If I draw in the tangent line at a point on the curve over here on the left, what we basically see is that the curve curves up from the tangent line. So the tangent line is below the curve. And if it curves up from the tangent line, we are going to call this concave up. And then if we have a tangent line for which the curve curves down from the tangent line is above. When we curve down, that's going to be called concave down. So that's kind of your definition from pre-calculus on concavity. Now, I do want to kind of talk about different things. So you can be an increasing function in concave up, an increasing function in concave down. You can also be a decreasing function and concave up. A lot of times students kind of have a little bit of trouble with that, but when you're looking at the fact that my function itself is decreasing, what do we know about the slope or the first derivative? Our first derivative, f prime of x, would be less than 0, and that's because f is decreasing. Okay? But when I look at the tangent lines to this curve, you will see the same behavior, that the tangent line, the curve curves up from the tangent line. So this is a concave up section. And if I'm going to look at my second derivative, which is what's coming up, my second derivative, because it's concave up, is going to be positive. It's decreasing, but at an increasing rate. You're accelerating. Your rate is getting faster. Now, when you look at that, and you might want to be, well, why is that happening? Why is my rate getting faster? When you look at your actual derivative function, because the second derivative is positive, that would mean that f prime is increasing. Okay? And so what's happening is, even though f prime is negative, it's increasing, which means it's getting less negative, heading toward 0. And so it's still a concave up graph. So this is where we're looking at this idea of how can we use information about the second derivative. We can use the second derivative with an increasing decreasing test to determine what f prime is doing. And we can use the second derivative as a concavity test to determine whether f is concave up or concave down. Alright, so just kind of review, this is pre-calc again. We're just looking at a graph and determining the open intervals on which the graph is concave up or concave down. So, and we're kind of assuming that we're giving you right now that right here at B, this is going to be what we call a point of inflection, a place where it switches concavity. C is going to be a point of inflection. And then we have a cusp here at D. And over here at E, we have another cusp. And then P is going to be a point of inflection. All right, so now notice that I did not label, say for example here, if we're looking at what's happening, this is concave down, this is concave up. So it did switch here at this cusp. But notice that I am not labeling that as a point of inflection, okay? From your textbook, your definition for a point of inflection is going to be that first you have to have a function that is continuous on the open interval, and C has to be a point in the interval, so we definitely know f of C must exist. Okay, so obviously you have to be a point to be a point of inflection. But it also has a requirement that the graph f must have a tangent line at x equal to c. Another way to think about that is we have a cusp right here where you are switching concavity, but we do not have tangent lines at cusp. This would be where we have f prime of c does not exist because at x equal to c there is a cusp. However, notice here that they did not, in the actual definition of point of inflection, say that the derivative does not exist, because you can have a vertical tangent line where the derivative would not exist, but yet it is still going to be a point of inflection. So if I had a graph that came in, became vertical, and then went on like this, where it's concave up and then concave down, this would be considered a point of inflection where your first derivative does not exist. That is okay. That is still going to be considered a point of inflection. However, a cusp is not going to be considered a point of inflection. So we definitely need to pay attention to that as we are working through the concavity test that we're going to be looking at. So that's our definition for a point of inflection that we want to be cognizant of. And well, also I need to add here, so the point must exist, it must have a tangent line, and the concavity must switch, okay? This is your pre-calc definition. Concavity switches at x equal to c. Now, we're going to talk about the calculus reasoning for how we determine that concavity switches, but right now that's your pre-calc definition that we have. So if I am going to basically come up with a derivative, or sorry, with a open intervals for which we're concave up and concave down here, then what we could do is we could simply list those out. We would say this graph is concave up, and usually we're just going to list them. It would be concave up from B to C. It would be concave up from, comma, D to E. It would be concave up from E to P. And yes, I am going to split that right there because the derivative does not exist at E, so it's not really considered concave up through the whole thing. So we're just going to split that, and that would be it. And then it's going to be concave down from A to B, from C to D, and from, I'm doing concave down, C to D, and P to Q. So that's fairly easy to kind of go through and list concave up and concave down. But again, make sure that you are paying attention to the actual definition of the point of inflection that we want to be careful of. Alright, so now anytime we talk about something changing, we're talking about the derivative. And so when we talk about the slope of the tangent lines of the function changing, we're talking about how the derivative function is changing. We want to know whether the derivative function f prime is increasing or decreasing. And so to determine where f prime, the derivative function, is increasing or decreasing, you would use the increasing decreasing test, which is to use its derivative. And its derivative is the second derivative. And the second derivative, if you recall from all of our notes and things that we've had before, is the acceleration. Acceleration is your change in velocity. Okay? So if the slopes of f, which means f prime, are increasing, then your second derivative is positive. If the slopes of f prime, are decreasing, then you know your second derivative is going to be negative. So basically we're saying we're describing the graph of f prime here. And then based on that, we know that when our slopes are increasing, then we know that our graph is going to be concave up. Now it may be positive, or it may be increasing in concave up, or it may be decreasing in concave up. That is determined by the sign of f prime. So if we have f prime as positive and the second derivative is positive, we would know that f is increasing and concave up. But if f prime is negative and the second derivative is positive, we would know that f is decreasing and concave up. All right, and so this is our concavity test, where we're going to use the second derivative in order to determine that. Now, places where you can switch concavity, let's think about that. We've seen in that example, which was a continuous graph, that you can switch concavity at places where your derivative, your second derivative is 0, but it's also places where your second derivative is undefined. You can switch at either a cusp or a vertical tangent. All right. Now let's kind of go through, if I've given you some information, this is kind of also a preview of section 4.6 where we're getting into the curve sketching. I'm going to give you basically description of what this graph is doing, and your job is to determine what will the picture look like. So let's take a look at each of these parts and kind of work our way through that and see if we can reconstruct what the graph of this and sketch the graph. So we're given that the first derivative is positive on this interval and negative on that interval. So what this tells me, let's kind of remember we're all about what the original function is doing. So what this piece of information tells me, because it's about the first derivative, and this is the increasing decreasing test, f must be increasing on negative infinity to 1, and f is decreasing on 1 to infinity. So that's what we know about our function right now. And we know that the function itself is switching from increasing to decreasing at x equal to 1. And so a place where you switch from increasing to decreasing, if it's a continuous function and that point exists, that would be a candidate for a possible extrema on that. All right. Then we have our second derivative, and it says our second derivative is positive for negative infinity to negative 2 and 2 to infinity. So that's telling us that f is concave up for negative infinity to negative 2 and 2 to infinity. Now I can also infer something else from this, because actually from the second part, where the second derivative being negative is going to tell me that f is concave down. And that's for negative 2 to 2. So essentially what we're looking at here is, I basically know right at this moment from this information that the function f was also differentiable for negative infinity to infinity based on both I and 2I, because at all values except possibly 1 I found a derivative. So it was derivative everywhere except maybe 1. And then when I look down here, I see that there was a second derivative at x equal to 1 down here, which means that there must have been a first derivative there, and which means that f must have been defined there because you can't have a tangent line if you don't have a point. So there's no discontinuity on this. So f is differentiable everywhere. And so that then comes back that I can then, based on this information, know that f has a relative max at x equal to 1 from this information. And we also know that basically looking at our -2 and 2, because we are switching concavity there, that there are probably going to be points of inflection, not vertical tangents and not cusp because of the differentiability. So there's going to be points of inflection at x equal to plus or minus 2 on this graph. Now we also know that the limit as x goes to negative infinity of f of x is -2. So that's telling me this graph has to have a horizontal asymptote at y equal to -2. All right, let me label it f has. Notice I'm trying to be very cognizant that as we are doing this, I'm not using the word it or the function. I'm specifically talking about which function I am referring to, which is I'm not talking about f prime, I'm talking about f, the original function. So I want to be very careful about that. And then we also know that, and this is on, I should say, on the left end, because it was going to negative infinity. And then here we have the limit as x goes to infinity of our function is 0. So f has a horizontal asymptote at y equal to 0 on the right end. All right, so now I think we're pretty much ready to go ahead and start sketching our graph. So I add my axes in, and then I kind of look at this and start putting some critical pieces of information in. The horizontal asymptotes are probably pretty important. So let's go ahead and draw those in. So I need one at -2, and I'll put my scale on in a second, and I need another one at 0. So I'm going to add this in and put that in for my horizontal asymptotes. All right, and this is 1, -1, and -2. All right, we know that it has to be increasing from negative infinity to 1 and decreasing on 1 to infinity. So we'll start sketching it. Let's see also what's happening here. We have a point of inflection at -2 and 2. So let's put in our -2, our -1, our 1, and our 2. So from negative infinity to -2, looking at our overlap here, we need to be concave up and we need to be increasing. All right, now sometimes when we're doing this, we actually might utilize a sign chart to help organize this information. I'm going to put f double prime here, f prime here, and then I'm going to talk about what f is doing. All right, my critical values for f are going to be at 1. All right, let's put 1 over here. And that first derivative, it had to be 0 there because we've already determined it was differentiable everywhere. And we know that before 1, and sometimes when I start doing this, because I'm going to be adding multiple information on here, I put a whole bunch of these to know that it's positive before 1 and then negative after 1. So that way it helps when I put the second derivative's critical values on there, or the possible points of inflection. So then we had points of inflection at plus or minus 2. So I'm going to add those in. I'm just going to change color here. So here at 2, we had a point of inflection. And then over here at -2, we have a point of inflection. And our second derivative is going to be concave up on the outside, so it's positive up to here, and then positive over on this section. And I know that in between -2, it was 0. Now I don't really know what the second derivative is at -2. It may be either D and E or 0. We'll worry about that later. I'll just put a question mark kind of right there and there for now. There's not enough information that I have to figure that out. Now I'm going to come down here and just write down what's the graph doing. The graph here from F prime, it's increasing and concave up until I get to -2. And then put a little line. We'll figure out what that is in a second. And then you go here. Now it is increasing, but it is concave down. Right. Then we have both of them are negative. Both the first derivative is negative and negative. So now I'm decreasing and concave down. And then here I am going to be decreasing, but now I'm going to be concave up. And then we've already talked about that there must be a relative max right here, a point of inflection here, and a point of inflection here. So we can organize it with a sign chart, and then we just want to come over and sketch it. Now, it says a possible one. We don't know how high it's going to go. All we know is that on this side it's got to be approaching -2 on the left end. So maybe I'll just kind of add it in here. And it has to be increasing and concave up until I hit -2. So maybe we'll do this. And it's okay to cross horizontal asymptotes. Remember, that's not a requirement that you don't cross them. So that gets to there, and I'll put a point because I'm going to show that's a point of inflection. But then I want to still be increasing and concave down. So that's going to get me to here. We're going to have a relative max at -1. And then I want to be decreasing and concave down all the way out here to 2. So maybe I'll just make this a little bit more curved to here. Oh, now I'm going to end this. Let me back that up. I'm going to end this because I have to be decreasing the whole time. So I definitely need to be decreasing to this asymptote. And you'll kind of see I had to go above this horizontal asymptote to get up here. So that now as I'm decreasing, I got to stay above so I can approach it. So I'm decreasing and concave down. And now I have to be decreasing and concave up. And you can see I'm approaching my horizontal asymptote on that side. So the idea here is to get the important features of the graph. That it was differentiable for -infinity to infinity, which also meant f is or was continuous for -infinity to infinity. I've got my switch in concavity at -2 and 2. And yes, I'm drawing this, it looks a little vertical, but remember, steep is not unusually steep. I'm assuming that this just might have maybe a positive slope of 100 at that point. That does not mean that it's vertical. I'm leaving it so a little slanty right here at this point of inflection. You have a relative max here. Oh, I can totally just, good thing I checked my work there. I'll fix that. Where was my relative max? My relative max was at 1, not at -1. Read my graph well. So come back over here and then over here. So that fixes the problem I have there. Good thing we all have erasers. And so this graph satisfies all the requirements that we had. All right, so again, definition of point of inflection. It's called an inflection point if the graph of f changes from concave up to concave down or vice versa, okay, at c f of c. So the sign has to change from positive, the sign of the second derivative has to change from positive to negative or from negative to positive. And make sure you add back in, because this is from your textbook, that you also want to make sure that f must have a tangent line at x equal to c, which means that you can have no discontinuities, which should be obvious, and you can have no cusps. However, a vertical tangent line is perfectly fine. All right? Concavity can change at a discontinuity, but it will not be an inflection point. And your possible inflection values are going to be places where the second derivative is 0, okay, or where the second derivative, because second derivative equal to 0 would be a max or min on f prime, which would mean that f prime switches increasing, decreasing, which is going to mean that f switches concave up and concave down, okay? Or the second derivative is undefined, and notice that's just why it's saying possible. The second derivative is undefined because that's going to be a possible, and notice it says as long as f of c is defined, and I'm going to add and f has a tangent line so that we can be in line with what your textbook says. All right? Not every possible point of inflection is an inflection value, and a chart, sign chart, is going to help us. All right, so let's take a look at example 3. So we're going to do the concavity test, and we're going to determine the open intervals where it's concave up or concave down, then find any inflection points. Now we're picking graphs that you already know. Sine of x plus 3 is going to have inflection points at pi over 2 and pi and 3 pi over 2. Well, sorry, actually at 0, pi, 2 pi, and so on, because you can picture your graph of your sine graph being switched up, being shifted up 3. But we're going to do this using calculus. So we're going to find y prime, which derivative of sine is cosine of x. And then we're going to find y double prime. The derivative of cosine is negative sine of x. All right? Now, what we know when we are looking at this is, was y differentiable everywhere? Yes. So y was differentiable everywhere. So it's differentiable on 0 to 2 pi. And definitely going to give us this idea that there is no place where I have a vertical tangent, no place where I have a cusp. So on my concavity, if the concavity switches, okay, if the concavity switches, then we know that there must be a point of inflection there. So I'm going to take my second derivative, and I'm going to set it equal to 0. So these are possible inflection points, So the second derivative equals 0 when negative sine of x equals 0, or when sine of x equals 0. And sine of x equals 0 at x equal to 0 plus pi k, which in the interval that we're interested in is basically 0, pi, 2 pi, and so on. So if we take a look at basically start creating a sign chart, and also kind of knowing that y double prime exists for all x. So I don't have any of those. So let's take a look at our sign chart. Now notice on this sign chart, I'm not going to do what I did above and put the first derivative on. I am only going to put the second derivative on because we're only worried about concavity. I'm not worried about whether the function f is increasing or decreasing. And I might want to use the notation that I have since I haven't named this f. Let's call this y double prime and y. So our possible point of inflection, don't call this a critical value. A critical value is specifically set for first derivatives. So a possible point of inflection in our interval is 0, pi, and 2 pi. Okay? And we're only interested in these values on our sign chart, so we can kind of ignore what's happening here and what's happening here. I'm leaving them on mostly because we're going to have consideration about what's going on here. So we have our second derivative. We want to know whether it's positive or negative in between 0 and pi. Well, the second derivative is a flipped sine graph. And since sine originally is positive from 0 to pi, if I flip it, it's going to be negative there. And then we have our pi to 2 pi. Again, an original sine graph is going to be negative there, but we flipped it, so now this is going to be positive. And 0, 0, and 0. Now, when we start naming, I'm going to go ahead and do just right next to this. If we go over here, you should know that the oscillations of your trig graph, that would be kind of finishing it out. But I'm going to go dot, dot, dot because it doesn't stay negative the whole time. it alternates going out at all the quadrantal angles on the x-axis. Now, what is y doing? Now, this is where you gotta be careful. Don't say increasing or decreasing. Y is going to be concave up, concave down, concave up, and concave down. So my points of inflection, places where the graph existed and had a tangent line, but where my concavity switched, these are now going to be my locations of my points of inflection. All right. Now, since we're only doing the graph from 0 to 2 pi, I am not going to include 0 and 2 pi because I don't have a switching because this is now gone, right? Remember, because we're limiting our graph to not start until here at 0 and to end at 2 pi, that would not be considered a point of inflection. Just like you can't have extrema, local extrema at endpoints, you can't have a point of inflection at an endpoint because it can't switch. So our answer to this, our final answer, is going to be y is, remember they don't interpret your sign chart, you have to answer it. So y is concave up for pi to 2 pi because y double prime was greater than 0. There's your calculus reason. Y is concave down for 0 to pi because y double prime was less than 0. And we would say that there are points of inflection at x equal to pi because your y double prime switched signs. Notice I really don't care which way it switched, not like I do for relative extrema, but it switched signs and y exists for x equal to pi. Or if I had named it f of x, I could have said f of pi exists. Because we want to make sure that we had a point and it switched. All right, let's take a look at B. Sorry, now in B, this is a fraction, but there's no division by 0 because of our x squared plus 3 is never 0. So our domain on this one is negative infinity to infinity, and this is going to be differentiable everywhere. So all the points exist and they all have derivatives. So f prime of x is going to be negative 6 x squared plus 3 to the negative 2 times 2x. Let's gonna have to use product rule to get the second derivative. So the second derivative, think of this as negative 12x. So negative 12x times 2 x squared plus 3 to the negative 3 times 2x plus my x squared plus 3 to the negative 2 times the derivative of negative 12x, which is negative 12. Now we're definitely going to work on this and make it a little prettier. You do have two terms being added together here and here, so we are going to do our factoring. Look for the common factors. I can take out a negative 12. I can take out an x squared plus 3, and the lowest power would be negative 3. So I pull that out. Here I'm going to be left with an x, and maybe let's highlight a little bit so we don't forget any. There's an x, a 2 left. That's gone. There's a 2 left here and an x. So I basically end up with being left here a 4x squared. And then over here, remember you're subtracting your exponents, negative 2 minus negative 3. Negative 2 plus 3 would be 1. So we get plus x squared plus 3, and the negative 12 got pulled out. So that leaves me here. So we can simplify inside and write this in a nicer form. On the top, I'm going to have negative 12 times 5x squared plus 3 over x squared plus 3 cubed. So that's my nice form of my second derivative. All right, so now what we're going to do is we're going to determine the possible points of inflection, which since the function was continuous and differentiable everywhere and its derivative or its domain was negative infinity to infinity, everything that makes the second derivative equal to 0 is going to be a possible point of inflection. And so we set the top part of this equal to 0 and we get nothing because 5x squared plus 3 does not equal 0 for any x. So there are no possible points of inflection. All right, so I just caught the beauty of live video. I just caught a mistake I made. When I took the derivative up here, the derivative is -2 times this, so I'm missing a negative right there. So make sure you add that in, and then when I add that -2 in, that's going to give me negative 4x squared. And then let me fix here. -4 plus x squared is going to be -3x squared. All right, so let's come back. I had to pause there because I was like, there's no way I would have given the second example that did not have point of inflection. I had to find my algebra mistake. So when -3x squared plus 3 equals 0, x squared equal to 1, or x equal to plus or minus 1. There we go. And again, it doesn't have any DNEs because the denominator, x squared plus 3, is never equal to 0. All right, so we're going to do our sign chart for the second derivative for the concavity test. I'm going to put f double prime and f, my possible points of inflection. All right, and that's where my second derivative was 0. We test each of the intervals in between. So if I put in, now obviously this is positive, this is always negative, and so I basically need to figure out this part right here. If I put in, say, -10 and square it, that's 100, but then that's -300, and a negative times a negative is positive. If I pick 0 and plug it in, this will be positive times negative, so negative. And if I pick, say, 10, by same reasoning as before, we get that. So what we know about f is concave up, concave down, and then concave up again. And since it existed, the original function existed and had points, and the derivative existed here, then we know that those are going to be points of inflection. The graph was differentiable, f was differentiable everywhere, so if it switches, then we know that if our second derivative switches, we have a point of inflection. So our answer for this one is going to be f of x is concave up for -infinity to -1 and 1 to infinity, because f double prime of x is greater than 0. F of x is concave down for -1 to 1, because f double prime of x is less than 0, and then our points of inflection, x equal to plus or minus 1, are points of inflection, or locations of points of inflection, because f of f prime of plus or minus 1 exists, and f double prime of plus or minus, I don't really want to say that. I want to say, and f double prime of x switches signs at x equal to plus or minus 1. All right? So now I kind of got away with saying, I said f prime of plus or minus 1 exists, which means that there was a tangent line there. Oh, now I really can't say that, right? Because that would then take out the that would take out the vertical one, because at x equal to plus or minus 1, there are tangent lines. And has a tangent line there. Okay, get all those reasons in there. All right, so hopefully that is kind of helping you see kind of where we're at. I'm going to look at C, one more for you. So in C, all right, so let's take a look at C. Now in C we want to be careful, because if we look at the domain here, we know that x cannot equal plus or minus 2. So because we have a domain restriction, we are discontinuous at plus or minus 2, and it's a non-removable discontinuity. There are vertical asymptotes there. Those values cannot be extrema or points of inflection. So you want to keep that in mind as we are kind of going through this. All right, so let's do our derivative. So g prime of x is going to be, using our quotient rule, our low d high minus our high d low all over our low squared. I am going to simplify this because I have to take the second derivative, so we're going to work that out. I can factor out a 2x. I'm left with x squared minus x squared, which will go away, and negative 4 minus 1, which is negative 5, over x squared minus 4 squared, which is going to end up being negative 10x over x squared minus 4 squared. So now we're going to take the second derivative using the quotient rule again. So we have our low d high, so x squared minus 4 squared times negative 10 minus high negative 10x times the derivative of the low. And I'm going to give myself more room here. What I ought to do is just... Alright, so I've rearranged it to give myself a little bit more room here. So I took the derivative, so I have low d high minus high d low, and make sure you use your chain rule, over the low squared. Now obviously we definitely want to simplify this, so we are going to look for factoring. Again, I'm going to go to the highlighter so I can help us out here. We have a negative 10 in common to both of these, and we have the x squared minus 4 in common to both of these. So I am going to pull those two factors out. So let's go to our pen. Negative 10 and x squared minus 4, and the lower power is obviously 1. What I have left inside is x squared minus 4 here, because I took away one of them. And then over here we're going to have an x, a 2, and an x, so this is going to be minus 4x squared. Minus 4x squared over my x squared minus 4 to the 4th. Notice I have a common factor top and bottom, so I can subtract or basically just cancel one out. So I'm going to do that. So I have negative 10, and then on the bottom now we're going to have x squared minus 4 cubed, and then we have x squared minus 4x squared, so negative 3x squared minus 4. So now that we have this in a nice form, so I saved myself some room here, I'm going to come over here, and now I need to find my possible points of inflection. So I'm going to set my second derivative equal to 0, and when I set my second derivative equal to 0, this is going to occur when negative 3x squared minus 4 is 0. which would give me x squared equal to negative 4/3. Let's double check. Right, sorry, interrupted by a little phone call there. So we get here and we realize that there are no x values where g double prime of x equals 0. So we have no possible points of inflection on this. But remember that I talked about this earlier, that when we're doing the concavity test, while I have no points of inflection, there is a place where you can switch concavity that is not a point of inflection. And coming back to our domain that we did up here, it can switch concavity at your vertical asymptotes. Now, you definitely know that the second derivative does not exist for x equal to plus or minus 2, right? Because of the derivative, second derivative having a division by 0 problem. But here we want to make sure, again, just like we did for the extrema, this is not a possible point of inflection because it was not an actual point on the original graph. However, if I'm trying to do the concavity test, I am going to put negative 2 and 2 on my sign chart because those are going to be places where the original function f can switch concavity. It just is not a point of inflection. So we're going to put in, I'm going to put D and E here. And then I like to, if I know what's going on, label what they are on F. Those are vertical asymptotes. So I'm not going to consider them for points of inflection, even if the second derivative switches. So then we do our test over here, kind of looking at this. If you recognize that this negative, and if I were to factor a negative out here, it would really be 10 and 3x squared plus 4 over x squared minus 4 cubed. That this is always positive on the top. So I'm really only looking at the bottom. And so if I pick a number like negative 10, that's going to end up being positive for the second derivative. If I pick 10, that's also going to be positive, and in between, it's going to be negative. So that tells me that f is concave up, concave down, and concave up. So even though the second derivative switches, we are not going to say there are points of inflection at negative 2 and 2. What we would say here is we would simply answer the question about concavity, which is f is concave up for negative infinity to negative 2 and 2 to infinity because f double prime of x was greater than 0. And we will say that our f is concave down for negative 2 to 2 because f double prime of x is less than 0. There are no points of inflection because there are no points on f, no points, let's say, that exist on f, where f double prime of x switches signs. Notice you're going to be tempted to say switches concavity there, but remember this is AP Calculus and you must give a calculus reason. Alright, so now in this set of notes, I'm going to stop right here, kind of break it up, let you take a break. And then we're going to come back and we're going to look at a few more examples of some special cases and some things that we do want to be careful of. And then we're going to talk about the second derivative tests for relative extrema.